Okay. Well, I figured I should teach you something about hash tables over the course of the semester, since it's probably all you use these days. So, just the context. Last few weeks we've had some lectures about amortized, some lectures about randomized. There's sort of different versions of worst case analysis with some notion of average built in. So today we'll talk a little about hash functions. I'll reintroduce Markov's inequality because we'll actually use it this time. We didn't use it last time. And then on the algorithm side, we'll talk about hash tables. I'm sure you guys already kind of know what that is. And then we'll talk about this really cool thing called the heavy hitters problem, which is also a really nice application, simple application of hash functions, and one that sort of at least blew my mind when I first learned about it. So, all right, let's see. All right, so I'm sure you guys have probably all looked at this web page before. This was, at least at some historical point in time, whatever web page Python uses to describe dictionaries, right? So, those brackets and stuff. Maybe you didn't even know they had a name, but they're just maps, right? They just do key-value pairs, and they're just your complete workforce for everything in Python, right? You just use that for everything, and you just make up fields, and you just keep going, and life is so much better that way. And it's a workforce for everything. I mean, their object system is just hash maps in disguise, right? It's just pre-populated fields in a hash map. So it's not like they really, yeah. So dictionaries are ubiquitous in Python. Python is sort of interesting because it makes it so convenient, right? It gave it its own notation. So you never have to write give me a new hash map or something like you would in other languages, right? You can just say, this is what we're all going to use anyway. We'll just provide it by default, and everyone loves it. Here would be the more verbose version for Java, right? So this is just the interface for a dictionary, interface for a map, where this is typed, so it's depending on your key type and your value type. I'm not sure. Have you guys looked at this before? I've seen this page a million times, but I'm older than you guys, so I don't know if you guys still use Java as much. All right, so anyway, so dictionaries, maps, key value stores, I think we all know what we're talking about. We just want to maintain key value pairs and be able to insert some key value pair, delete the pair associated with a key, and then look up the value associated with a key, and those are the main operations. All right, so we're just going to first think about how to implement that. Okay. So, all right, so I know you guys know what the eventual solution is, but still work with me pedagogically. So, all right, so as far as this kind of key value problem goes, here's a special case that comes up a lot in class, right? What if all the keys are just integers between 1 and n for some fixed known n, right? And this actually happens quite a lot. Roughly all the problems we've done in this class have all been static problems, right? It gives you a graph or something in step 1, right? So you can, in step 1, just go through and label all the vertices 1 through n, and now you just have fixed indices 1 through n for the rest of the problem. And it didn't take you very long to label the vertices. That only takes linear time, right? So a lot of static problems, you actually automatically have this kind of setup where all the keys are known ahead of time. They're already kind of slotted nicely between 1 and n. All right, so if you wanted to supply something like a dictionary for this special case where the keys are between 1 and n, what might you do? How would you make a dictionary when the keys are integers from 1 to n, and n is known, it's fixed? Just an array. Okay, so just... I thought I wrote something. What's going on? All right, 1 sec. Okay, finally figured it out. Sorry. The simplest thing is to just have an array with n slots, and then you're using big O of n space, right? So 1 slot per key. And you're having constant time access, right? You can't really do any better than that. So that's perfect. Okay. Another case Right, so that's perfect for the static setting when we can just reindex the input once ahead of time. But it's not so great for like a dynamic setting when the keys are changing a lot, right? And keys come, keys go, and they're not just organized from 1 to n. So, all right, so what happens more generally, right? So in general, your n integer keys may come in from a much larger space. Okay, so for example, maybe your keys are strings, right? They're strings of characters. And strings of characters can be thought of as numbers by looking at the corresponding bits, right? I can think of that as a very, very large number. Like take the ASCII and each letter is some 128 base digit or something. Okay, so now even if you only have n keys, the point is it's coming out of a much larger space, not just the integers 1 to n. And so if we use our, we could just reuse the idea of, why don't I just make a huge array? Right? And the good news is you do get constant time lookup and operations. But the obvious downside is that your space usage is proportional to all the possible keys, like 1 through this capital U, which could be the gajillion, whatever, instead of something proportional to the actual number of keys that you have, right? So what might be a deterministic, obviously we'll do hash tables in a moment, but not that, what would be an alternative way to implement a dictionary, right? Where these keys are sort of spread out. They're not nice and compact. They can be anything really. Yeah?
A linked list?
Okay, you can make a linked list, right? And I can keep them, I guess I don't have to even be in sorted order, right? So I can just list the keys, and if I want to look up a key, I just crawl through the list and find it, or I conclude it's not there. Okay, so the space usage would be great, right? Because you'd have one spot in your list for each of your keys. So you'd be using n space, and that's fantastic. What would be the downside? It can be slow. I mean, you have to scan the whole list just to find what you're looking for. I guess by the same token, you could use those array lists that you thought about in the homework, for example, where it's backed by an array, but it's still basically a list. But at least arrays are a little bit faster sometimes. They're more cache friendly. Okay, so what else besides a list can get you really good space, but better search, better insertion, deletion time? Okay, we can do a binary search tree, right? Like the ones we did in class, or really there's a lot of different choices. But any of these kind of self-balanced trees, these trees that maintain a height of log n or something like that, and take log n time for operation. Okay. And a nice thing about a tree is that, you have one vertex per key, so you have n vertices, n edges, the size is n. But the running times are like log n. Okay, and that's still much better than a list. So those are our two basic kind of deterministic approaches, right? So arrays have fantastic running time. Constant running time, that's perfect, right? You can't ask for anything better because it's just like, give me the 10th item, I'll go to the 10th item, right? The 10th slot in memory. But the problem is that the space usage is based on the range of the keys instead of the number of keys. And the search trees have great space. It's really one more key, one more node. So the space is perfect. And the running time is not bad. Log n is pretty good, but it's not as good as an array either. Okay? So the question we're asking in this first part of class is, can we get the best of both worlds? Can I get something that's, a constant amount of space per key, but has running time more like a constant as if it was an array? Okay? Can I get like array-like performance, but in a space-efficient way? Okay? And so the answer is yes, with the use of randomization. Okay, and we're only going to look at one very simple example, and there's other chapters in the notes on more sophisticated versions that are actually used in real life, but this is partly teaching. So, okay, so a big important idea, and the main thing with this class is the idea of using a hash function. Okay, So hash function is going to map integers to integers. But in general, it's going to map a really large range of integers, between 1 and a gazillion, to a smaller range, like between 1 and 100, or something like that. Okay, so, and ideally, like each of those 1 billion possible keys will get kind of mapped in a really random looking way to one of the 100. Okay, that's the high level idea. Well, if you're going to map a billion things into 100 slots, you're going to have a lot of collisions. Right? No matter how evenly spread it, you're just going to have a lot of collisions. Collisions means two of the keys map into the same slot in a smaller space. Okay. So, so much for that. So, an ideal hash function is one that where every single one of the inputs, one of the billion, is mapped to one of the smaller set, one of the 100, uniformly at random and independent of each other. Right? And I mean, that's like as random as it can get. I just go through every possible input key 1, or the input key 1, I just choose sample one of the 100 independently. Input key 2, I'll choose one of the 100 randomly. Input key 3, I'll choose one of the 100 randomly, right? That's the most random possible function I can think of, right? And so we call that an ideal hash function, because it's probably what we often imagine hash functions to actually be. It's the simplest way to think of it, right? Because everything is completely random. Okay. But these are actually a little bit too good to be true. Does anyone want to take a stab at why? So there's something very nice about assuming all the keys are completely independent and random from each other. Like if you're going to analyze it later, that's the strongest assumption you can have in your favor. But it's actually too much to ask for to be practical. Does anyone want to try to guess why? Yeah?
In real life in general, if you insert two different data points at similar times, then there might be some relation between them, just because they're in the same time area.
Well, okay, so that's kind of, well, okay, there's a different question of where do random bits come from in general. You know, if you're getting like, random number generator is not truly perfectly random. But even if I assume I have access to truly random bits, for the sake of discussion. Because at some level we make some clarifying assumptions. So we assume we have access to some random bits, typically. And then there's a whole subject called pseudo-randomness that discusses some of those more grungy questions. But if I assume I have access to random bits for sake of this ideal conversation, there's still some issues about an ideal hash function. You still have collisions, that's fine, but that's going to be true of all ideal hash functions. So okay, maybe let me give you more of a hint. So I'm going to claim that to write down an ideal hash function, you're going to need a lot of bits, like n log k or something. Okay, so the claim is that to be able to write down an ideal hash function, it's going to need a lot of space. N log k is a lot, right? Because n is the size of the universe, right? So that's saying for every billion, you're basically writing down one of the IDs. Okay? But the claim is that you can't compress it anymore. You have to use a lot of space. Yeah.
Is it like when you have a collision, you need to like make sure like which value, or like you have to store the keys somewhere inside there so that you know which
I think you're thinking ahead to what if we use it in a hash table. So I'm actually still a step back, which is simply why I can't even write down a hash function like on my computer. So even just having a hash function, actually, for building a hash table, an ideal hash function is sort of perfect because basically the more randomness the better, because it will evenly spread things out. We'll talk more in a moment about that. But actually, it is truly ideal in the sense that it's actually not practical, but not because it wouldn't. If we had it, it would have worked great. But I'm saying we can't have it because it would actually require a lot of space to write down. All right, let me ask a different question. So if you're sampling from the distribution of ideal hash functions, right? So that means you say, oh, computer, give me an ideal hash function, it gives you one, right? And that function can be one of a large number of functions from mapping things between 1 in a billion to 1 in 100, right? How many possible functions could be among those that are returned? So it's randomly constructed, but it does give you back a fixed function, right? It's randomly constructed, but once it's constructed, it's fixed. N to the k, right? So it can be any one of the n to the k possibilities, right? Because we know that any key can get mapped to any value independently of the others. So any combination is possible. There's n to the k combinations, right? Because there's k choices for number 1. Oh no, it's not n to the k, is it? There's k choices for the first one, there's k choices for the second one, k choices for the third, all the way down to k choices for the n. That's not actually n to the k, that's... What is it called? Okay. Last week of class. All right. It's actually k to the n. Okay. So there's k to the n possibilities, right? Okay. Now, each of those functions needs to be written down and expressed as a bit string. Right? Somehow it needs to be represented on the computer with bits. Right? And two different functions need to have two different bit strings. Right? So how many different bits, how many bits, so there needs to be k to the n different bit strings. Right? So how many bits do I need to express 2 to the n, k to the n bit strings? Which is to say k to the n different functions. Yeah. Yeah, n log k. So, 1 bit can express 2 bit strings. 2 bits can express 4 bit strings. 10 bits can express 2 to the 10 bit strings, right? So we take the log base 2, right? So actually, if you did want to sample from the space of ideal hash functions, you would need, from an ideal distribution that can give you any possible function, you would actually need n log k space just to write down the function, right? And that's a lot. So we don't actually have access to ideal hash functions, even though they're sort of the simplest to analyze, right? Because everything's completely random. But we don't actually get to use them. So, in its place, what we sometimes do, or what we have to do, is we look at limited classes of hash functions. So we look at simpler functions that are somewhat random. They're not as random as every number getting assigned a completely random value. But they're somewhat random, and we want to figure out how much randomness I need for the application at hand. So today, and I guess for the rest of the class, we'll only worry about the bare minimum, which is called a universal hash function, okay, which only has the following property. So H is still going to be a random construction that's assigning each of the 1 in a billion to 1 in 100, okay, but it doesn't require completely independent sampling. Okay, so it doesn't require any 3 of these keys to assume any 3 of these values completely random or something like that. Instead, all it says is that for any 2 values, any 2 keys, the odds of them colliding needs to be, if there's 100 value possibilities, 1 in 100. As if those 2 were kind of spread out randomly, right? But it's not saying that all n are getting mapped completely randomly, independently of each other, to one of those 100 values. Right? It's just saying that somehow they're getting mapped in some random way, so that any 2 keys, the odds of them colliding are as if they're random. Right? So it's only in one perspective they're random. So let me give you a concrete example, and you'll see it's so simple that it couldn't possibly be that random. So the function just ax plus b mod p mod k, where p is some prime number bigger than k. Okay. A is this coefficient a is between 1 and p, chosen uniformly at random. Okay. And b is chosen between 0 and p minus 1, uniformly at random. Okay, so it's really just ax plus b modulo p modulo k. Okay, so this is not that random of a function, right? You just randomly sample a, you randomly sample b. And you just do ax plus b. So clearly, like if you know the value of some keys, you can figure out the value of other keys because it'll let you figure out what a and b are. So it's not like a completely random mapping from the keys to the values. It's a very simple function. It's randomly constructed. And you can show that this is enough randomness that the odds of any two keys colliding is 1 over k, where k is the space of values. All right, so there's a homework. I mean, it's not homework anymore, but there's an exercise going through it. In this class, I'm just going to focus on using it and trying to see why that first property, this universal hash function property, is strong enough for some really basic applications. Okay, so, but this is great, right? Because obviously ax plus b is very fast for a computer to compute. It's very fast. I mean, it takes very little space to store. You just have to write down a and b and p, right? So this has all of that fast and compactness property that you probably assume when you're using a hash table in Python or whatever. Okay, so that's a universal hash function. All right. Okay, so hash tables, right? How do hash tables work? Well, high-level idea. Again, we're just trying to do a key value store, right? So I just want to insert a key, delete a key, stuff like that. And the idea is to use that hash function to take your huge space of possible keys and map it into like a smaller array. Okay, and as far as like, what slot should this go into? I'm going to use my hash function to find the slot down below. Okay, so that's better in some worst case ways than something just like, if I have 100 slots, let me just take the key modulo 100 or something, right? Some simple deterministic thing. Because obviously, if the keys were like, if you had bad luck and you had like key 1, key 101, key 201, key 301, they'll all go deterministically to the same spot if you did something as crude as that. So at least if we use a hash function, there's a little bit more randomization and there's a little bit more hope that you won't get too many collisions. All right, so, okay. All right, so the only issue with this general model is that whenever we hash down many keys into smaller set of space, you're going to get collisions. And there's lots of different possible hash tables out there. And the main distinction between them is how do they handle their collisions. Okay, so I guess I left this space blank in case you guys want to suggest any ways to try to handle collisions in a hash table. Or address them or get rid of them or whatever. Any ideas? Yeah. Okay, so that's the one we'll talk about a lot today. It's called chaining. So I have a picture of it coming up, but the idea is that, if I have lots of keys going to the same slot, then I'll make a linked list here and just list them. And hopefully the list won't be too long because we won't have too many collisions, is the hope. So that's the simplest one. That's what we'll analyze today. Any other ideas? Yeah?
Generate a new hash.
Yeah, you could instead take these collisions and make a secondary hash table. I think that's here. Oh, that's different, but yeah, so that does exist, and actually there's something called perfect hashing, which is an exercise which is based on this idea. Anything else? Okay, well, one is try to make that bottom part so big that you probably don't get collisions, right? And there's always a question of how big should it be in that case. And then there's a lot of like funky ones. So I have a couple examples. So one is called where is this? Oh no. Okay, so one is called cuckoo hashing. So the idea, you'll have two hash functions, right? So every key can get mapped to one of two different value places. Okay? So with a particular key, you first check to see if they're both occupied, right? If one of them is free, then you can just put it there. Okay? But if you go down and you find they're both occupied, okay? So there's already some key in this slot. Okay? This key itself has two hash values, right? And this is only one of them. So you'll try to bump it to another and use its other hash. Okay, so everyone gets mapped to 2, and you're going to try to look for one empty slot in one of those 2. And if they're both occupied, you'll try to bump one, and for that guy that's getting bumped, try to use the other hash to find the other unoccupied spot, and then possibly keep bumping in like a recursive fashion. Okay, so every value is in one of two keys, and you try to find if one of the two are open, and otherwise you start trying to like bump things out into the other hash value. That kind of thing. Okay, so that's called cuckoo hashing. Another one, which I've taught in the past, but I won't do this year, but is actually, I think, the most common one in practice as I understand it, is, so you just have a big array. I mean, not a big array, but you have your array where you're going to store the values, and you hash it, right? And if that spot is already occupied, then you just start marching down the array until you find an empty slot. Okay, so ideally, your spot will be empty and you can just put it there like you want it. But if it's occupied, that array cell is occupied, you just keep scanning the array until you find an empty slot. Okay, so that's called linear probing. And that one I think is very good performance in practice, partly because scanning an array is very fast. Okay, it's a little bit tricky to show this works, which is why I won't have time to present it, but there's a chapter on it. But you guys should at least know what the algorithm is. Okay. All right, but today, we're still operating at a basic level, so we're just going to do the simple linked list version, which is sometimes called chaining. Okay? And we're going to analyze chaining while using a universal hash function. So what does that mean? So the universal hash function is, I've changed some of the notation. So down here, the size of the array has suddenly become m. Before I was referring to k, but now it's m. Sorry about that. Okay. So you have your big space of keys, and the first part is you calculate ax plus b mod p. So I've sort of generated this intermediate layer to represent that. And then from there, you just go modulo m, where m is the small space. Okay. All right, so that's the simple thing. And then whenever you have a collision, you just make a linked list there. Okay. All right, so in general, when you're using this data structure, if I'm like inserting, if I'm like inserting this key here, right? You first calculate ax plus b, right? And then you go mod m. And then, you have to go down the linked list and check to see if the key is already there. And if it's not, you put it at the bottom or something, right? So really, you have two constant time, just arithmetic at the beginning. That's not very hard. And then you pay time proportional to the size of the linked list, right? So for each operation, the amount of time you spend on the key is basically how many other keys are colliding with it, because that gives you the length of the linked list down at the bottom. So we just need to argue that on average, this is not so bad. Okay, so here is what we want to argue. So if you have n distinct keys, and you're using a hash table of size m, okay, so m is some value that fits in your computer, okay, your expected running time is roughly n over m, which is really to say the expected number of collisions of a particular key is n over m, as long as you're using a universal hash function. All right, so Okay, so how might we try to prove this? So imagine I'm inserting a new key, right? I want to analyze what's the expected number, and so let's say there's n keys in the table, and I'm inserting a new key. Okay, and so really I want to analyze is how many collisions do I expect on average? That'll be the expected running time because that's the average length of a linked list that you're running to. Right? So what is the expected number of collisions on average? Okay, why? All right, so let's say I'm inserting a new key I'll call K star, and let's say that K1 through Kn are already in the table. Those are the n keys in the table, right? Okay, so the expected number of collisions right? What should I do and why? Yeah.
You have xi be the event where K star collides with K I.
All right, so let's say, we can make an indicator variable. So we can imagine something similar to what we did with quicksort. So 1, if Ki collides with K star, and 0 otherwise, right? So collides means h of Ki is equal to h of K star, where K star is the new one. Okay? So the number of collisions is the sum from 1 to n of xi. Right? So now I'm looking at expected total number of collisions, but that total number of collisions has now been written as a sum over all the keys. And now what? Yeah, so wait, what was the fancy name? Okay, linearity of expectation. Okay. And so just to remind us, each of these is the probability of a collision, right? So it's the probability that your new key has the same value as the ith key already in the table. Sorry, that should be k sub I. Okay. And do we remember what the definition of a universal hash table was? I should have put it on the right side, but I forgot. Yeah, so the only thing I'm assuming about the hash function is that the odds of any two keys colliding is 1 over, well, it will be m down below up there. It's k. Okay? So you get n over m. Okay? And I wrote 1 plus n over m because you still have to also compute the hash. I mean, the 1 is just the extra constant mark. Okay? So on average, because each of those, the collisions, pairwise collisions are bounded, you're still able to do the expected analysis. Okay, so I think keep in mind that the hash function is incredibly simple. It's just ax plus b. Right? It's not that random. But it's enough to get this universal hash property. And the universal hash property, as limited as it is enough to pull off the linearity of expectation kind of analysis, right? So a lot has to do with average being such a simple quantity to deal with, right? And the fact that we can do things like linearity of expectation. We're not really asking too much of it, but we just ask for a good average performance. That's part of what's going on. All right, so there you can start to see why a limited amount of randomness, a very simple, weak hash function. This is not like SHA-2 or some crazy thing, right? A relatively weak hash function can get you good average performance. Okay. All right. Okay, so that's my first application. Although you guys have already used and probably understood hash tables at least implicitly for some time, so I think the next one should be a little bit different. So let me set it up. Oh, any questions about hash tables though? Okay. All right. All right, so I guess you guys have probably all seen this page before. Maybe you haven't. So there's this thing called Google Trends, and it will tell you what search queries are kind of trending, say, across the United States on a given day, especially like more than normal. So I think this slide I probably made in the fall, because I used this for the randomized class. So maybe, okay, so these were some of the trending topics. I guess maybe that movie Don't Worry Darling might have just come out or something. I think there was a soccer match that morning between Barcelona and Man City. I think Chet Holmgren just broke his ankle or whatever it was. I don't know if anyone follows basketball. Okay, he's like 7'2", but he's like super skinny, and LeBron James just ran into him and destroyed him. Yeah, I mean, Nick Cannon is somehow always trending because he has 1 million children or something. All right. Anyway, so you can go to this website. It's kind of amusing. It'll tell you things that are trending. I don't know what's trending right now. What would be trending? I don't know. Okay. All right. So, besides for the amusement of seeing what's popular right now, why does Google even have the infrastructure to do this, right? They want to keep track of trending caches and in general, what are the popular, they want to keep track of the popular queries and stuff like that so that they can cache your queries, right? So if you want to know why Google is so fast when you ask your question, it's because you're not that special and 1 million people have already asked your question, right? And they just saved the answer and they're just ready to serve it. Okay, so they're not searching the whole website in the blink of an eye. They're just giving you some answer that someone already asked. Okay, that accounts for 99.99999% of queries or something, right? So there's, and this is not just Google search. You can imagine any other application, right, where it's important to keep track of sort of that dominant subset of queries, okay, so that you can have a good cache system and stuff like that. But what's sort of perplexing is that, Google is such an open-ended thing, right? You can search anything, right? And obviously they can't have a counter for every possible arrangement of ASCII characters, between 1 and 1,000 characters long or something, right? So, at some level the question is, how are they able to keep track of these things when there's so many different things to keep track of? Right? So that's sort of an interesting thing. I don't know, does anyone have any ideas?
Each query is small. Not each query some value with small range.
It's true, but okay, so you can try to maybe collapse queries, understand which queries are synonymous and stuff, but that only get you so far. I mean, it's still, the question is, basically every possible different meaningful query should give you a different counter. And I feel like you can still generate many distinct meaningful queries, even if you're able to address things like capital letters throwing you off or, obvious synonyms or something like that. Still, every different meaningful query would require a different counter. There's so many different things. So that's not necessarily it, though. I'm sure they do some of this, right? They probably also do some, NLP style projection and stuff. But anyway, we won't talk about that. Okay. All right. So let me try to frame the problem a little bit more formally. Okay. So this will be an example of a different model of computation we haven't discussed before, and probably the only time we discuss it. But it's kind of an interesting model. Okay. So it's a model that is appropriate for really, really large data. So big that maybe it doesn't fit in your computer, right? We often imagine, I just have a file and I can read over it again and again and again. But suppose it doesn't fit in your computer, right? And so imagine that the elements is presented, you're doing something based on elements in some really, really long list that doesn't fit in your computer. So the elements come one at a time, right? Like the queries come in one at a time, one at a time, one at a time. Okay? And in principle, the list is so long you can't store it in your computer. So you just want to like examine a little bit of data, maybe take some notes for yourself, and then go on to the next element. Right? So we're trying to make algorithms that use space that's going to be independent of the size of the input, or relatively independent. And so in this sort of space-constrained model, we want to identify the quote-unquote heavy hitters. Right? So I've simplified this to just say, oh, there's each element is some key, okay, from some big space. And I just want to identify which keys occur really often. Right? So like something like a 5% quote-unquote heavy hitter, those are the keys that happen at least 5% of the time. Okay? But it could be lower, it could be 1%. You know, even if you did like 1 in a billion or something, you could fit a billion keys in your computer probably. So 1 in a billion may be a practical thing in real life. Okay? But the point is that we're only interested in the heavy hitters for some fixed threshold. Okay. So, okay. Right. And so what makes this problem interesting, obviously in a normal setting, you can just write down all the things and you can just go through and count everything and no big deal, right? It would be a trivial problem. But what makes this problem interesting is that we want to identify all the heavy hitters but use much smaller space. I don't want to use space proportional to the input size. Maybe something proportional to the output size, right? Or something smaller, right? Like, I don't know, square root n or log n or something, if all the elements are like an integer between 1 and n. Right? But the point is this will scale much better with the size of the string. It doesn't depend on the length of the string. Okay, and that's what makes this problem interesting. Okay. Right. Okay. So, just to help us brainstorm a little bit, right? This seems like an impossible task, right? I'm trying to count up and identify the most important out of an input that's so big it doesn't fit in my computer. Right? Well, but what are some maybe high-level reasons for optimism? The obvious objection is that there's so much, yeah.
I mean, there's a good chance that the heavy hitters in any subsection of the stream might be representative of the overall global heavy hitters. So,
yeah, if I look at one cross section, you could hope that it's a good representative, and maybe a cross section fits in my computer. Okay, well, that may or may not be true in real life. You probably would want to test it somehow. It's close to intuition, although we'll still want to get worst case bound, so I don't want to make that strong of an assumption. But there is this idea that maybe if I sample the stream, if I'm thinking about elements that appear a lot, I have a good chance of my sample hitting those elements or something, right? Maybe that's some intuition. But like, yeah.
If the keys have the same value, there's no reason to store both of them.
Okay, so in this problem there's no values. You're just looking at a stream of keys, and the question is just which of the keys occur at least 5% of the time.
So in that case, you could just put a counter on each one.
We could put a counter on every key. But the number of possible keys is huge. So I want to do something better and much more space efficient than counting every key. But I'm only worried about the keys that occur at least 5% of the time. Yeah.
Divide the input into parts and kind of like trying to get some statistics about each part.
Well, okay, so if the input size is really big, I feel like you have two problems here. On one hand, okay, so the question is, can you divide it into parts and process them separately? Now, we only have one computer in this model. Okay? So there's two possibilities. One is, if you make the parts small, so you can do a really good analysis over one part, then you'll be dividing your stream into a ton of parts. Right? Which means that you'll be saving up statistics from a lot of parts. There may be so many parts you can't save statistics for every part. So suppose the input size, suppose your computer had size like k, could fit k into the data, and the input was much bigger than k squared. So if you divided the input into parts of size k, you would be storing more than k pieces of information, one for each part.
You can read that.
Fine, but you're going to have to store the information. Yeah.
Okay, so like, I feel like we can take advantage of the fact, like, kind of following your intuition earlier, that like we're trying to find these heavy hitters and are going to be more of them because they're heavy hitters. So like, I think it's something where we have an array like size k, and every time we get an input, we pick a random slot and we put the items there, and then we continue doing that for all the items. And the idea is, like, if there's a lot of them, it's likely that in this end-up array that we have, there will be some of them, right? So it's like we can replace items in this array every time we have like the equivalent of a collision. And the idea is that, like, because there's a lot of these heavy hitters, like the likelihood is that there will be some of them left in this array once we're done. There's going to be some sort of analysis on this.
Okay, so I think that's good intuition. Maybe I'll generalize a little more. In a lot of maybe random experiments we can imagine doing over our data, where sort of that has any kind of majority rules sort of thing, where something that occurs more often is more likely to win your random experiment or something. The heavy hitters should have an advantage because they occur a lot, right? So we can try to take advantage of that. I think that will, in hindsight, appear. Let me ask you a question. Okay, so one thing that came, the natural suggestion, why don't they have a counter for every element, right? Well, there's too many different elements. So that's out, that's thrown out. But, you could say, oh, can we have a counter for every heavy hitter? That would so almost be necessary, not actually necessary, but to identify the heavy hitters, you probably want to have some estimate of how many times they occur or something, right? Okay. But you might think, okay, that's still a lot of counters. How many heavy hitters can there be? How many 5% heavy hitters are there in this tree? 20 or less. Why? Yeah, each one occupies 5% of this tree. Okay, so maybe one reason for hope is that there's only 25% heavy hitters, and in general, whatever the percentage is, if it's 1%, there's only 100 of them. If it's 0.5%, there's only 200. Okay. So this is something to look out for, is that the output size is small. The input size is big, but at least the output size is small. So at least just hope that you can at least represent the output of your computer or something. At least there's some semblance of hope. Now there's two other reasons why we have some hope. Okay? One is that we're going to use randomization and allow for some small probability of error. So if you're really looking at a huge stream and you're only preserving a subset of information, right? You're throwing some information out and you're taking some guessing. You're probably going to introduce some likelihood of error, maybe a small chance depending on how clever your algorithm is. But as soon as you start throwing out some information, right, which you have to do because you can't hold on to everything, right? You run this risk of, oh, did I throw out something that I wish I hadn't? Something that doesn't look like a heavy hitter early on might become a heavy hitter later, and you're just missing some bits because at the time it didn't seem like a big deal, right? So we're going to allow for a small controlled probability of error. Okay. And the other thing we're going to do is that we're going to introduce some kind of approximation guarantee where I allow some margin of error, and I'll explain that when we get there. Okay? So at a high level, between those last two parts, we're not going to try to be too perfect. Okay? I'm going to allow myself some tiny chance of possibly making a mistake. It'll still be under control. We'll be able to analyze it. And I'll have some margin of error. Like maybe I want to produce a list that A, includes all the 5% heavy hitters. Okay? And maybe has a few extra by accident, but still guarantee that all the extras are at least 4% heavy hitters or something like that, right? So you have a few extra, and you wish you didn't have the extras, but at the very least they're close to 5%. And maybe that's good enough for your application, because to get a perfect list of all the 5% heavy hitters is maybe too much to ask for in such limited space. Right? You only have one pass over to data and stuff like that. Okay, so we're going to allow those two things. We're going to relax the model a little bit, and we'll get something practical out of this. Okay. All right, so we need to introduce one more tool to use this. This will come up near the end of it. But I know we discussed this before, so I can be brief. This was part of that really long, boring probability lecture a couple weeks ago. But this is Markov's inequality, right? So I think the example I gave in class was, what fraction of the class can get 2 times the class average on the midterm, no matter how low the midterm score? And the answer is at most half. Okay, otherwise the average would be higher. Same with what percentage of the U.S. population earns 2 times the average national income, or what fraction of the NBA players score 2 times the league average, which is probably like 8 points or something, right? And it can only be at most, because beyond that point you start to increase the average. It doesn't fit. Okay? 2 can be replaced by any factor alpha. What fraction of the class can get 10 times the class average? At most 1/10. Okay? All right, let's go back to this heavy hitters thing. All right, so you're given these keys one by one. Okay? We want to use sublinear space. Okay? And from now on, instead of doing 5% heavy hitters, it'll be some epsilon heavy hitters for some fixed value of epsilon. So 5% will correspond to epsilon at 0.05, but it could have been 0.01, it could have been 0.001 or something, and we'll get bounds depending on epsilon. We'll probably need more space if epsilon is even smaller, right? Because it's better. Okay. All right, so we're going to we're also going to kind of work on a slightly more general problem. Okay. We're going to try to estimate the relative frequency of every element in the stream. Okay? So absolute frequency of some key is how many times it actually occurred in the stream. Relative means how many times divided by the total length of the stream. So what percentage of the stream does that element represent? Okay? If we can figure out, or if we can approximate everyone's relative error simultaneously, right, then we should be able to identify all the heavy hitters. Right? So if I wanted all the 5% heavy hitters, and I was able to estimate the relative frequency of all the elements, plus or minus 1% or something, I can just list everyone with relative frequency at least 4 in my data structure, because that will capture, a little buffer for the 1% error, something like that. Okay? So if we can estimate the relative error or relative frequency of every element, then we should be able to extract out the heavy hitters afterwards. All right, so we want to estimate the relative frequency of every element. Okay, so, we want to estimate all the relative frequencies up to some fixed epsilon additive error. So maybe it's 1%, so I'm allowed to be off by 1% for any particular element. It could be 0.5%, it could be less, right? And as we've discussed many times, I don't actually have space to count for every element. Okay? So I want to estimate every element up to 1% error. I don't have space to have a counter for every element. Okay? Oh, rats. Okay. All right, so that would seem impossible, given that we don't have enough space for every counter. The one saving grace is that 0 is a good estimate for almost all of the elements. Right? So if I'm allowed 1% additive error, so I'm allowed to be off by 1%, right? Only 100 elements have relative frequency at least 1%. Everyone else has a relative frequency less than 1%. So if I just report 0 for everyone else, that would be fine. Right? So while at first it might seem like, how am I going to keep track of a counter for every element to get everyone's relative frequency? The great thing is that by allowing for 1% error, it also means that I actually don't have to keep track of every single element perfectly. Because most elements, almost all elements, have relative frequencies so small that 0 is a perfect estimate for them. Okay? So this is great. So allowing for a little bit of error takes this impossible problem and makes it possible. Okay? And if we don't like the error, we can still make it smaller to a point where at least, it's practical for us. Okay? The only question, of course, is that ahead of time, I don't know which ones to actually keep track of. So I know that I really only have to keep track of about 1 over epsilon elements, because those are the elements with at least epsilon relative frequency. But of course, the basic problem is I don't know which elements those are. Okay, so that's the question. All right, we're doing well on time. Does anyone have any ideas of how to solve this problem? So I want to, ideally I can roughly count all the big elements and ignore the small elements. But I don't know which elements are going to be big and which elements are going to be small. How do we solve this riddle?
But we can use first we can map all the elements to the small,
Okay.
like 1 over epsilon.
Okay, so we can try doing some hashing, right? So I'll take all the keys and hash them down to a smaller array.
Yes, we can count the order or number of order elements because it's small.
Okay, so we can have a counter for every, so imagine making a small table of counters. Okay, maybe something like 1 over epsilon or 10 over epsilon. We can increase by a constant. So imagine making a small table of counters, what you're describing. And so given an element, I'll hash to some random spot and then increase that counter or something?
Yes. And
Okay.
focus on the biggest elements among them.
Okay.
After finishing.
But I still have to figure out the biggest element among them
Biggest elements in
in a particular slot.
particular slot.
Yeah.
But there are not so many.
Okay.
So many times the last one.
Well, the input size was originally gazillion or something, right? And something huge, right? Effectively infinite. And then you've made 1 over epsilon slots, which if epsilon is 0.1, that's like 100 slots, right? So each of those slots is still taking in, on average, an infinite divided by 100 elements. So it's still big. You've only divided by 100.
But
And you have to do it for all the slots simultaneously. Still, it's not a bad idea. So that's actually what we're going to explore. Oh, ideas? Okay. All right. All right, so here's what we'll do then. We'll basically do something kind of like a hash table, right? So what we're going to do is I'll make it a little bit bigger. I'll make it like 10 over epsilon sized array, and I'll just have a counter. And for each key that comes in, I'll map it to wherever it gets to on the hash function sends it, and I'll just increase that counter.
I believe I hope that the probability of that heavy hitters are in the same slot is very low.
That would be great, right? So this is big enough where you're hoping that most of the heavy hitters won't collide. We'll need to analyze that. Okay. Okay. All right. So the basic data structure is kind of simple. Okay, it's just like a hash table of counters instead of linked lists. So I'll make a smaller array of size like 10 over epsilon, and I'll have a counter in each one. When a key comes in, I'll go to the hash counter and I'll just increase it by 1. Okay? So each counter is really counting up the total number of elements with that hash key. What is that hash value? Okay. Right. Okay, so that's the high level idea. Okay. And now if I want to estimate the frequency of like an element I or something, okay, I'll just go to wherever the counter is and return that value. Okay, so, sorry, this is sort of wrong. If I want to estimate the frequency of element I, I'll go to the hash table and do what the hash table wrote down for that slot. Okay, so that means every element is probably getting overestimated because its corresponding slot accounts for its own tally plus everyone else that collided. Okay, so this will overestimate elements. And the only question is how much will it overestimate elements? Does that make sense? All right. Good? Okay. So, let me just set up our analysis. So I'm letting W denote the size of the smaller array. Like I think of it as a width, which is going to be like 10 over epsilon for us. Okay. A is that array of counters. For an element I, I'll let Fi denote the true frequency of the element. Okay. H will refer to our universal hash function. Okay. And M is the length of the string. So there's n distinct keys, and the total number of keys coming in, including repetition, is m. So m is some astronomically large number. Okay. All right. Good. Okay. So, all right. So let's look at a particular element I. We stated that it's always going to overestimate. Right, that hash counter for element I is always going to overestimate the true frequency because it's including the collisions from other possible keys. Okay, so the first side of this inequality is actually automatic. Okay, so that hash counter for element I is always going to overestimate the true frequency. It'll never underestimate it. The more interesting claim is the other side, right? How much are we going to overestimate the count for element I? This says that it's going to be epsilon over 5 times m. Okay, so in relative terms, in terms of relative frequency, where you divide everything by m, you'll be off by epsilon over 5 with probability 1/2. Okay, so you have a half, 1 in 2 chance of being off by at most epsilon over 5. All right, so we want to show, let's try to figure out how to analyze this, right? We want to analyze the probability that h of I is bigger than f of I plus epsilon over 5m, right? That would be bad if it was, maybe I'll write strictly more, right? This is the bad event that I want to show happens with probability at most 1/2. Okay? All right, so I want to argue that I don't overestimate by more than epsilon over 5 times m with even, 1/2 probability. All right, how can we try to go about this? Well, okay, sometimes it's good to, first of all, I have a typo here. This should be AHI. Sorry about that. Okay. Sometimes it's good to at least look at the expected value of whatever we're analyzing, right? So let's maybe as a preliminary step, try to figure out this step. right? So this is what is the expected value for this hashed overestimate. Okay. So what is this? Well, how would I calculate this? I'm sorry? Okay, so I think you're thinking of some kind of collision style analysis like we just did. Okay, so let's see. Okay, so if I'm looking at how many, so it will definitely include its own count, right? So f sub I is always there, plus by linearity of expectation, I'll sum over all of the other indices j not equal to I. Okay? And if it collides, then you'll add fj, which is the frequency of item j. Right? So I'm summing over all the other keys. What are the odds that it collides? And if it collides, then we'll also add its frequency to the count. And okay, fine. So what is this? What is the probability for a fixed j? Yeah, well the k here is a w. Okay, so this is over w. Okay, so w is the size of our smaller table down below. It's a universal hash function. So the odds of it colliding are like 1 in... Oh, you want this? Okay. Sure, you can have it. I'll give it to you. Doesn't upset me. All right. Now w was equal to 10 over epsilon. So just flip that upside down. Epsilon over 10, and summing over all the other elements f sub j. What's a simple upper bound? This sum is a little ugly. How can I get rid of it? If I sum over all the elements,
is it relative frequency?
These are all absolute frequencies. These are all absolute.
Absolute? No.
Yeah. So the actual count. M is just the length of the stream minus f sub I, but that's okay. We'll give up a little bit and throw in an inequality. Okay, so M is the length of the stream, right? The number of items that showed up. N is the number of different keys. And as usual, we use the only two letters that look and sound the same. So M is the length of the stream. N is the number of keys. Okay. Yeah. Bad habits die hard. Okay, so, all right, just look at the expectation. So we know that AH of I is always bigger than Fi, greater than or equal to Fi. And it's at most Fi plus epsilon over 10m in expectation. Right? Which is just saying that all the other frequencies are kind of evenly spread out down below. So we'll just, add the expected amount to I's count. Right? Okay, good. So the expected value is good, right? Because I want to get epsilon over 5m, and the expected value is less. It's epsilon over 10m error. Right? But now I want to show that's going to be at most epsilon over 5m with probability at least 1/2. Okay. Let me rewrite this a little bit. Okay, what if I did this? AH of I, what's the probability that I did nothing but subtract Fi from each side, but now what it's saying, like the left side is how much the count overestimates Fi. It's always some non-negative number, right? Because it's always greater than or equal to Fi. And the right side is, so it's saying, what are the odds that the overestimate is by more than epsilon over 5m? And maybe I'll ask you guys first, what is the expected overestimate? What is the average overestimate? Yeah, okay, but work with me. What's the average overestimate? Epsilon over 10m. So it's really saying, what are the odds that the overestimate is at least twice the average overestimate, which is at most 1/2 by Markov's inequality. Okay, so the right-hand side is 2 times the average of the left-hand side, and the left-hand side is non-negative, so you can use Markov's inequality. So it just becomes how many students get twice the class average? What are the odds that you get twice the expected overestimate? It's at most 1/2. All right, we're gonna finish on time. Don't worry. All right, so good. So what does that mean, right? We have this really, really simple data structure. For any single element, right, the overestimate is pretty small, epsilon over 5m or something, was probability at least 1/2. So any element with probability 1/2, you have a good estimate, right? So any single element, you have a good estimate with probability 1/2. Now the only issue is that we want to estimate all the frequencies with like a really, really high probability, right? So getting any particular element with probability 1/2 is far from getting all the elements at the same time, right? So the question is, how can I amplify our bounds, right? So I have something that works on a particular element half the time, and I want it to work for all the elements all the time. And maybe as a first step, suppose for one element, I just want it to work way better than half the time. How can I just make my simple data structure much, much better? How can I drive down the probability of error? Okay, think of it this way, right? Think of this data structure as a coin flip, right? It has a 1 in 2 chance of being right. You flip a coin, you get heads, it's correct. If it's wrong, it's tails, right? I really just want to get 1 heads. Suppose, yeah. Okay, we could increase the size, but it won't make that dramatic of a difference. So if I had replaced 10 over epsilon with 100 over epsilon, then I can get this to be like 1 over 20 instead of 1 over 2, because it will increase by a factor. But basically, you've increased the size by 10, and you decrease the probability of error by a factor of 10. I actually want to do something more dramatic than that. All right, in the interest of time, here's the answer. All right, so it's just this, you guys all know this, right? Like, if I flip one coin, the odds of it being tails is just 1/2. If I flip 2 coins, the odds of them both being tails is 1/4. If I flip 100 coins, the odds of them being all tails is 1 over 2 to the 100, right? These streaks just plummet, right? It goes down to 0 very fast. So we're going to take advantage of that by just making many copies of our data structure. Okay, we'll make like log n copies or something, but we'll figure out that in a moment, right? Now for a particular element, if we make a lot of copies, the odds of them all screwing up is low, right? Because that's like flipping a bunch of tails in a row, okay? Now if you make a bunch of copies, I know we're over time, if we make a bunch of copies, right, and some of them are wrong and maybe one of them is right, how can I get the right answer? So maybe a lot of these data structures are overestimating your thing by too much. Maybe one of them is good. How can I identify the good one? We can take the minimum, right? So if we return the minimum over all the data structures, it'll get you the best one. Because they're all overestimating. And whichever one is overestimating the least is the best one. Okay, so we can return the minimum. And this is only going to screw up if all of them screwed up, right? But the odds of that is like 1 over 2 to the however many copies you make. Okay, so let me wrap up. No more rhetorical questions, right? So if I make like 10 log n copies of the data structure, the odds of a single one failing becomes like 1 over 2 to the 10 log n, which is like 1 over n to the 10. Right? So by using log n space, I get probability of error 1 over polynomial in n. Okay, it goes down to 0 so fast. And beyond that point, now I want to make sure all of them are correct. Right now, any single one is correct with probability 1 over n to the 10 or something. But now the probability is so low, I can take a union bound. So the probability of any of them being bad is at the most the sum of one of them, any one of them being bad, right? So you have n different keys. Each of them is wrong. Bad was probability 1 over n to the 10. So overall, your probability of having any error for any element is at most 1 over n to the 9. Okay, so just independent copies drives down the probability so fast that you can take a union bound at the end. In conclusion, this is really the conclusion. At the end of the day, you only need log n over epsilon space. That's much smaller than the size of the input stream, right? This is actually kind of a practical quantity. And you can estimate the frequency of every element up to epsilon error. And that's it. But you need to use hashing. You need to use randomization. You need to introduce some error for all this to happen. And I think that's it. All right. Sorry for going over. Last class next time.